Welcome to the ePathshala lecture series in computer science. We are looking at the computer architecture course. This module is on a case study of multi-core architectures. So the learning objectives are to discuss about the shift that has been brought in the computer architecture industry to multi-core architectures, and to discuss the salient features of one of the multi-core architectures, namely Intel's multi-core architectures. So if you look at the performance history of the various architectures over many years, in terms of the number of components that are being used, the clock speed, your performance, the power that has been dissipated and so on. This is a graph that shows the performance information. Now, if you look at the observations that can be made, you know that the number of transistors have actually doubled every 18 months, complying with the Moore's law. But the process frequency has been flat between 3 to 4 gigahertz. So, the frequencies were periodically increasing, but beyond a certain point the processor frequencies have not increased too much, and you find that power has hit a wall because of the power density that has been shown here. Because of the power that is dissipated, you have what is called the power wall problem, which we have discussed in many modules. And you also have rising temperatures because of the increased power density. So, as the power density increases, as this diagram shows, you find that even heat which is equivalent to the temperature at the sun surface or the rocket nozzle can be generated. So, that has basically put in a check to all the improvements that we were looking at in terms of increasing the frequency and so on. And ILP improvements are obviously not resulting in performance gains anymore. So, we were forced to shift to multi-core architectures, and this is a typical multi-core architecture where instead of just having one execution, one processor, you have multiple cores of execution. All of them sit on the same die, and because they sit on the same chip, you have interconnect delays are not too heavy. And each of these cores can also support multiple threads of execution. What has been shown here is one core supporting 2 threads of execution. So, depending upon the number of cores that you have, you can have multiple threads of execution happening simultaneously. So, multi-core architectures try to exploit all types of parallelism that we have discussed. Each of these cores will try to exploit the instruction level parallelism, and they also have multiple threads of execution. So, they will also try to exploit thread level parallelism, and depending upon the support that you have for instructions, you can try to look at SIMD extensions available here. So, you can also have support for data level parallelism. So, there has been a paradigm shift to multi-core architectures, and multi-core is a reality now. So, whether you are looking at personal mobile devices, desktops or servers, multi-core architectures are there everywhere, and your free performance ride is over. You can no longer just keep increasing your clock frequency and try to expect to have an improvement in performance. So, there is no automatic performance gain. And if you look at these multi-core architectures, you can either look at them as a homogeneous architecture or a heterogeneous architecture. Homogeneous architectures will have the same types of cores which are replicated. Suppose if you are looking at a quad core processor, and if all the 4 cores are identical cores, then it is an example of a homogeneous processor. On the other hand, if you look at a heterogeneous architecture, you will have different types of cores. Remember, we mentioned this name with respect to our GPU architectures also, where you have a CPU which is of a different type, and if you have a GPU which is an accelerator there for graphics related instructions for exploiting data level parallelism, it becomes a heterogeneous architecture. So, likewise, when you have multiple cores, and if each of these cores are different, or at least if one core is different from the others, it becomes a heterogeneous style of architecture. And software technologists will need to understand the architecture properly to get performance gain out of these multi-core architectures. And with dual core and multi-core processors, the architectural issues that we have been discussing earlier would be different from the traditional issues. And the new performance mantra is of course performance per watt. And we are going to look at 3 different case studies. One is with respect to Intel's multi-core architectures, then we look at Sun's Niagara processors, and we will also look at IBM's Cell BE processor. NVIDIA architecture, the GPU architecture which we discussed in the earlier module is also an example of a multi-core architecture. So, if you look at Intel's architectures, Intel, you know that starting from the x86 architectures, you have had a lot of processors that have come in, and even in 2004, as early as 2004, Intel acknowledged that it had hit a thermal wall, and it disbanded one of its most advanced design groups and said it would abandon 2 advanced chip development projects. So, now Intel is embarked on a course already adopted by some of its major rivals, that is obtaining more computing power by stamping multiple processors on a single chip rather than straining to increase the speed of a single processor. So, this was the information that was published in New York Times on May 17, 2004. So, that indicates the journey that Intel has taken. So, this indicates the Intel architecture evolution. So, starting from your x86 architectures which evolved into your Pentium family, then you had the dual core architectures which were introduced, core duo architectures which were introduced in 2006, and then you had the quad core architectures, and then starting from 2008, the most popular architecture that you have is the i7 processor, i7 architecture, which is follows the Nehalem architecture. So, as a case study, we are going to look at the Intel's i7 architecture. So, the salient features of Intel's architecture are hyperthreading technology, turbo boost technology, improved cache latency with smart L3 cache, new platform architecture, a quick path interconnect which is very effective, intelligent power technology, higher data throughput via PCI Express 2.0 and DDR3 memory interface, improved virtualization performance, remote management of network systems with Intel Active Management technology, and other improvements like increase in window size, better branch prediction, more instructions and accelerators, etc. Now, we look at each of these salient features in more detail. So, the first one that we look at, so when you look at a dual core processor, and if you have only one thread being supported by each of these cores, you have through 2 threads of execution. And when you look at a quad core processor with 1 thread of execution in each of these cores, you have 4 cores of execution. Now, when you look at multi-core processors with hyperthreading, each of these cores can support 2 threads of execution. So, you can actually look at 8 cores of execution. So, hyperthreading basically is the ability for the hardware and the system to schedule and run 2 threads or processes simultaneously on the same processor core, and it enables simultaneous multi-threading of up to 2 threads per core, and it obviously reduces the computational latencies, and it makes optimal use of every clock cycle, and this helps run demanding applications while maintaining the system responsiveness. Simultaneous multi-threading is a concept that we have already looked at. So, hyperthreading is basically looking at using this concept. So, hyperthreading technology looks like 2 processors to software. Though you actually have only 1 core of execution, there are 2 threads. So, you have 2 threads of execution, logically 2 threads of execution per core. And when you have 4 processors, you have 8 cores of execution. The second technology advancements that they brought in was the turbo boost technology. Now, this turbo boost technology provides a performance boost for lightly threaded applications and also optimizes the processor power consumption. See, when you look at 4 threads of execution, 4 cores that are available, and all 4 cores are actually going to be used because you have so many threads of execution available, then you can run all these threads on all 4 cores of execution. But suppose if you have a lightly threaded application, you do not require all the 4 threads of execution, then you can run it on 1 or 2 cores and you can run it at a faster rate. So, that is basically turbo boost technology. You can run some of the cores at a higher level, but at the same time you will have to make sure that the power requirements, the power that is dissipated, the heat that is dissipated is everything within limits. So, this is an innovative feature that automatically allows active processor cores to run faster than the base operating frequency when certain conditions are met. The duration of time that the processor spends in a specific turbo boost state depends on how soon it reaches the thermal, power and current thresholds. So, the power, current and temperature limits are continuously monitored, and when the thresholds have been reached, it will just put them back into their original base mode of operation. So, Intel Turbo Boost is activated whenever the OS requests the highest processor performance state, and the maximum frequency of the specific processing core on the Core i7 processor is dependent on the number of active cores, and the amount of time the processor spends in the turbo boost state depends on the workload and the operating environment. So, this is a pictorial representation of the turbo boost technology. So, when you look at 4 cores, a quad core processor, you can have them operating at a base frequency, or you can have all 4 cores operating at a slightly higher frequency, that is possible, or you can say that only 2 cores can operate at even much higher frequencies, or you can say that a single core can operate at a high frequency compared to the base frequency. So, depending upon the number of threads of execution available and how much of performance improvement is required, you can just make some of the cores operate at higher frequencies compared to the base frequency of operation. To give you an example of how much of what is the base frequency like and how much you can actually improve the frequencies, if you look at a quad core, the base frequencies are normally around 1.73 gigahertz, and the maximum turbo boost frequency is around 2 gigahertz. And when you are looking at only 2 active cores, you can look at 1.73 as a base frequency, and you can go up to 2.08 gigahertz. And if you are only trying to boost up one core, then if it is a single core, and you can go up to even 3.06 gigahertz. So, that is the turbo boost technology, and all the time when you are boosting the frequency of a particular core, you always make sure that your thermal requirements are satisfied, your power requirements are satisfied and the current requirements are satisfied. If it goes beyond the threshold, then you bring down the frequency. So, the third technique that we are looking at is improved cache latency with the smart L3 cache. Normally, if you look at an exclusive cache, an exclusive L3 cache performs cache snooping to search the local caches of other caches if data is not available. Because you know that if data is not available in L3, because if it is an exclusive cache, even if it is not available in L3 cache, it might be available in some other caches, some other local caches of the other cores. So, you definitely have to search for the local caches of other cores. And this you know that it gives you a problem because of the snooping associated with that. You may unnecessarily have to do a lot of snooping that you will have to do. Now, when you look at smarter and larger, the smarter L3 cache which is used in the Intel's i7 processor, it uses an inclusive shared cache. Inclusive shared cache that can be up to 12 megabytes in size. When you say that it is an inclusive cache, then you know that whatever is available in L2 will also be available in L3. So, if you find that L3, there is a miss in L3, you are sure that it is not going to be available in the local caches of the other cores. So, you do not have to go check the other cores. So, you have to go to only main memory. So, the unnecessary snoops that you have to do are automatically reduced, and the L3 cache is shared across all cores, and an inclusive shared L3 cache guarantees that if there is a cache miss, then the data is outside the processor and not available in the local caches of other cores, which eliminates the unnecessary cache snooping. And inclusive nature helps increase the performance and reduces latency by reducing the cache snooping traffic to the processor cores. So, this is the new memory hierarchy. So, you normally look at new three level cache, which consists of an L1 cache, where you can look at a 32 KB instruction cache and a 32 KB data cache, an L2 cache per core for very low latency, 256 KB per core for handling data and instructions, that is normally a unified cache, and the third cache is shared among the various cores. It can be an 8 MB fully inclusive, fully shared, and all applications can use the entire cache. This gives you a diagrammatic representation of the cache hierarchy that is found in your i7 processor. So, the next innovation that we are looking at, or a salient feature that we are looking at, is the new platform architecture. So, previous Intel microarchitectures for a single process system included three discrete components, namely the central processing unit, your graphics and memory controller hub GMCH, which is also known as a north bridge, and an IO controller hub ICH, which is also known as the south bridge, and these two put together is normally is the chipset. And the front side bus, the FSB, was the interface for exchanging data between the CPU and the north bridge. And if the CPU had to read or write data into the system memory or over the PCI Express bus, then the data had to traverse over the external FSB. In the new platform architecture, in the new Nehalem architecture which we are looking at, Intel moved the memory controller and the PCI Express controller from the north bridge onto the CPU die itself. So, this reduces the number of external data bus transfers that the data had to traverse, and this in turn increases the data throughput and reduces the latency for memory and PCI Express data transactions. So, this is ideal for test and measurement applications such as high speed design validation and high speed data record and playback. So, this is pictorially represented here. So, you can look at the previous generation microarchitecture on the left. On the right is the Nehalem microarchitecture, where you find that the memory controller and the PCI Express controller is integrated onto the CPU itself. And the moment they get integrated, the interconnect delay is going to be very less. You do not have to travel on the external transfer data on the external data bus. So, that definitely improves performance. So, the next important feature of Intel's architecture is the quick path interconnect. So, starting from a single bus that connected the various components and a dual independent bus and a hierarchical bus, Intel has moved on to the quick path interconnect QPI because that the compute platform has become very complex and you have more components generating a lot of data traffic, and you need to have a lot of communication happening between the cores, memory, subsystem and the IO. So, you definitely need to have an efficient method for moving data in order to improve the performance. So, if you look at the QPI, you have this is the architecture of the QPI. So, this architecture includes memory controllers integrated into the microprocessors, which are connected together with a high speed point to point interconnect. So, QPI gives you a point to point interconnect. The new Intel quick path interconnect provides high bandwidth and low latency, which deliver the interconnect performance needed to unleash the new microarchitecture and deliver the RAS features, reliability, availability and serviceability features, which are expected in enterprise applications. So, basically to give you a feel of what your QPI is, it is a high speed point to point interconnect between processors. So, you can see from the diagram on the right that every processor is connected to every other processor, and there is a simultaneous movement of data between the various components. There is support for several features like lane polarity reversal, so that routing becomes easier, data recovery and DC skew circuits, and waveform equalization that is the design of the high speed link. So, if you look at a processor with the QPI interconnects which has been shown here, the Intel QPI includes a cache coherency protocol to keep the distributed memory and caching structures coherent during the system operations. It supports two types of coherency. It supports both low latency source snooping and a scalable home snoop behavior. And the coherency protocol provides for direct cache to cache transfers for optimal latency. So, if you look at the QPI, it is a layered protocol. There are 5 layers which have been indicated here. The physical layer consists of the actual wires as well as the circuitry and logic that is required to support the ancillary features required in the transmission and reception of the ones and zeros. The unit of transfer that you look at in the physical layer is normally 20 bits, which is called a FIT or a physical unit. The next layer is the link layer. The link layer is responsible for reliable transmission and flow control, and the unit of transfer in the link layer is an 80-bit FLIT for flow control unit. The third layer is the routing layer which provides a framework for directing packets through the fabric. The transport layer is the fourth layer, which is an architecturally defined layer but not actually implemented in the initial products, and this provides advanced routing capability for reliable end-to-end transmission. And the last layer is the protocol layer. The protocol layer is the high level which gives you the high level set of rules for exchanging packets of data between devices. A packet is normally comprised of an integral number of flits. And how this QPI supports the RAS features, reliability, availability and serviceability features is what is discussed here. So, the RAS requirements are met through advanced features which include CRC error detection, link level retry for error recovery, hot plug support, clock failover and link self healing. So, there is a 72-bit CRC which is provided. This increases reliability and the bits are sent in line, which reduces the number of cycles required. And suppose if there is a clock failover, then a different lane can be used for transmitting the clock, and suppose if there is a link failover, there is a lane which fails, then the width can be automatically adjusted, and that is what is called the self-healing property. So, instead of transmitting the entire width, you can reduce the width of transmission and still transmission can happen when a failure is detected. That is the self-healing process. So, detection of failure and automatic readjustment of width automatically happens here. This basically increases your availability of the system. And detection of clock failure and automatic readjustment of the width and clock transmitted on a predetermined data line, thereby increasing availability. So, if a clock fails in one lane, then it is automatically shifted to another predetermined data lane, and suppose if that also fails, you also have another backup for that. So, that way you are able to handle clock failures. The next salient features is intelligent power technology. So, in this case, intelligent power gates allow the idling processor cores to near zero power, so that you can conserve power. So, power consumption is reduced to 10 watts compared to 16 to 50 watts that was seen earlier. And you have automated low power states to put the processor and the memory in the lowest power state available and is allowable in a workload. So, then when you are looking at data throughput, you can look at higher data throughput via the PCI Express 2.0 and DDR3 memory interface. So, PCI Express 2.0 data bus doubles the data throughput from PCI Express 1.0 while maintaining full hardware and software compatibility with your PCI Express 1.0. It has a maximum throughput of 8 gigabits per second either direction. Features multiply DDR3 1333 megahertz memory channels. You have a system with 2 channels of DDR3 1333 megahertz RAM and has a memory bandwidth of 21.3 gigabytes per second. So, if you look at the support for virtualization, virtualization enables, we have already discussed about the basics of virtualization. Virtualization enables running multiple OSs side by side on the same processing hardware. So, i7 has brought in a lot of features which will support virtualization. So, you have new features such as hardware assisted page table management and directed IO in the i7 processors and its chipsets, which allow software to further improve their performance in a virtualized environment. And if you look at remote management of network systems with Intel Active Management Technology, this active management technology provides system administrators the ability to remotely monitor, maintain and update systems. And Intel AMT is part of the Intel management engine, which is built into the chipset of an NLM based system. And this feature allows the administrators to boot systems from a remote media, track the hardware and the software assets and perform remote troubleshooting and recovery. The other improvements that are brought in Intel architectures, apart from the innovative features that we already discussed, are generally greater parallelism. So, what you mean by greater parallelism is, that there is anyway support for out of order execution, and when you try to look at out of order execution, the number of instructions that can be scheduled out of order will depend upon the window size. So, what i7 looks at is trying to increase the size of the window size and the scheduler, so that you can consider more number of instructions which can be executed out of order, scheduled at least out of order. So, that is the greater parallelism that we are talking about. You are also looking at efficient algorithms, and when you are looking at efficient algorithms can be written only when you have improved performance of synchronization primitives and you have faster handling of branch misprediction, and when you look at improved hardware prefetch and better load score scheduling. With support for all these happening, you are able to come up with efficient algorithms. And when you look at enhanced branch prediction, you have a new second level BTB that has been incorporated. You have a new renamed return stack buffer. Remember, we spoke about the return address predictors, return address buffers, which are used to store the return addresses when you come back from procedures. So, a normal data structure is not going to work in the case of a return address predictor. You will have to have a stack like arrangement. So, that is why it is called a renamed return stack buffer. You also have new application targeted accelerators and Intel SSSE4 streaming SAMD extensions for instructions. So, you have new instructions that have been added to enable XML parsing, and you also have at least 7 new accelerators that have been included, which will help you provide better performance. So, to summarize, we have looked at various factors that have led to Intel multi-core architectures. That is because we know that we cannot exploit instruction level parallelism further, and there is a power wall problem, there is a heat problem. So, all that has led to the introduction of multi-core architectures in the computer industry, and for the past 1 decade or so, we have multi-core architectures available everywhere. So, whatever type of system you are looking at, whether it is in the embedded domain, you are looking in the personal devices domain, or server domain, whatever it is, multi-core architectures are there everywhere. So, to look at the various types of multi-core architectures that are available, we just looked at Intel as a case study. So, the various features that we looked at Intel case study with i7 as the example architecture are hyperthreading, where you have multiple logical threads per execution per core. You look at the turbo boost technology, where in the case of lightly threaded applications, you can try to boost the operating frequency of a few threads so that those threads execute at a faster level. You try to look at an improved cache latency with a smart L3 cache, which is an inclusive cache, and because it is an inclusive cache, you are avoiding the unnecessary cache snoops that will have to be performed. Then we looked at the new platform architecture, which has enabled the integration of your memory controller into the CPU die itself, thereby avoiding the unnecessary data transfers on your external bus. Then we looked at we just had a quick introduction to the quick path interconnect, which is a point-to-point interconnect which allows all processes to communicate with each other. There is a simultaneous transfer possible, and it has a layered protocol. It supports cache coherency, and that it also supports the RAS features. And we also looked at intelligent power technology, where power has been drastically reduced. We also looked at how you can have higher data throughput through the PCI Express 2.0 and the DDR3 memory interface. We saw how you can have better performance, virtualization performance, and we also looked at how you can look at a remote management of network systems with Intel's AMT, and we also pointed at other improvements like increase in window size, better branch prediction, more instructions and accelerators, etc. So, these are the references. All the Intel white papers on i7 processor have been referred, and all the figures and materials have been taken from these white papers. Thank you.